Hey there and welcome. Today we're tackling a core concept in mathematics, function transformations. Ever see a really complicated graph and wonder how it's made? Well, it's actually way simpler than you might think, and by the end of this, you'll see how any graph can be built from just a few basic moves. Okay, let's dive right in. You see a graph like this and your first thought might be, whoa, where do I even start? I get it, it looks pretty intimidating. But what if I told you it's really just a simple, familiar shape playing dress up? A basic curve that's just been shifted, stretched, and flipped into place. The secret is a technique I like to call the building block method. Think of it like this. We start with a really simple foundational shape. Then we use a toolkit of transformations to move it, flip it, and stretch it into the exact graph we want. It's like construction, but for math. So first things first. Every complex function belongs to a family, and at the head of that family is what we call the parent function. This is our cornerstone, our starting point for everything. Here are four of the most common parents you're going to see. You've got the classic parabola, that's x squared, the absolute value v shape, the square root curve, and that cubic s shape. Getting these four shapes burned into your memory is the absolute first step. They are our fundamental building blocks. All right, now for our first tool in the toolkit, shifting. This is literally just how we pick up our foundation and move it around the graph without changing its basic shape. Let's start with the easy one, vertical shifts. That's just moving up or down. And this one is super intuitive. You add a number on the outside of the function, the graph goes up. You subtract it, the graph goes down. It does exactly what it looks like it should do. Horizontal shifts, though, this is where things get a little weird. It's completely counterintuitive. When you subtract a number inside the parentheses with the x, the graph actually moves to the right. And when you add inside, it moves to the left. Yeah, it's the opposite of what you'd expect, and it's a super common spot for mistakes, so watch out for this one. Okay, our next tool is reflection. This is how we take our graph and create a perfect mirror image of it across one of the axes. When it comes to reflections, it's all about where you put that negative sign. If the negative is outside the function, you flip the graph upside down, right across the x-axis. But if you tuck that negative sign inside with the x, you flip it sideways across the y-axis. The location of that one little sign changes everything. Let's move on to our final tool, dilation. This is how we stretch or squish our graph, making it wider or narrower. This table lays it all out pretty nicely. If you multiply on the outside, you cause a vertical stretch or compression. If you multiply on the inside, it affects it horizontally. And just like with the horizontal shifts, the inside stuff is counterintuitive. Multiplying by a big number like 3 doesn't stretch it out. It actually compresses it, squishing it in from the sides. So we've got our tools, right? Shifting, reflecting, and dilating. But here's the thing. The order you use them in is absolutely critical. You can't just do them in any order you want. And this right here is probably the most important rule in this whole explainer, the order of operations. You have to follow this sequence, no exceptions. First, you handle any reflections. Second, you do any dilations, the stretching and squishing. And last, and only last, you do the shifts. So remember, flip it, stretch it, then move it. That order is the key. All right, let's put our new toolkit and all our rules to the test. We are going to build that exact graph you saw at the very beginning. Our starting point, our parent function, is the simple square root of x. Nice and easy. Okay, first up in our order of operations is reflection. We look inside the function and, yep, there's that negative sign right next to the x. That's our cue to take the entire graph and flip it horizontally, right across the y-axis. Step 2 would be dilation, but if we look, there's no number multiplying our x or the whole function, so we can skip that. That brings us to step 3, shifts. Inside the function, we see x minus 1. And we remember our counterintuitive rule, right? Minus 1 inside means we shift the whole thing 1 unit to the right. And for our final move, we look at that plus 2 hanging out on the outside. That's a simple vertical shift. So we take our graph and lift the entire thing up 2 units. And there it is. We started with a simple curve, applied our rules in the correct order, and we have built our final complex graph. So building a graph is one thing, but what if it's the other way around? What if you already have the graph, but you need to find its equation? Well, we can just work backward. We can reverse engineer it.
We can totally deconstruct this graph to find its secrets. It's like being a function detective. First, what's the shape? It's a V, which just screams that its parent is the absolute value of x. Second, where's the new vertex, the point? It's at 2, 1. That tells us our shifts, right 2 and up 1. The final clue is the stretch. We just need to find one other clean point on the graph, like 0, 5, plug those numbers into our equation and solve for A, the stretch factor. And just like that, we've cracked the code.
So here's the main takeaway, the big idea. Don't be intimidated by complicated-looking graphs. They're all just puzzles. Every single one is built from a simple, familiar foundation using a consistent set of tools and a very clear order of operations. This process of building and deconstructing, that's the real key to understanding how functions work. So now you have the toolkit. The next time you see a complicated curve, don't just see a problem, see a puzzle. See if you can find the parent function hiding inside. Thanks for watching.